Little mic check here. Okay. Good morning. Um, so I'll say up front, I know those of you who are taking the architecture class and programming and algorithms too. Good morning, Captain Price. Good morning, Tyler. You're the only two I can see in the chat so far. Tyler, you're one of those for sure. But anyway, for those of you who are taking architecture and programming algorithms too, I know that this is a painful 2 weeks. I did my best at least to not have the two projects overlap, but I know that weeks when projects come due are busier than most, so it just is what it is. We don't have that many projects in the assembly class, just the two. But I know that you're, in terms of my classes, this is more work than normal, so just sort of got it out, I guess, and hopefully it goes okay. Okay, we're in October. So changes a month are also good ways to feel like we are progressing through the semester's work. So week 7. Oh, nice. Okay, so Captain Price has already done P&A 2. Yeah, I think so Tyler points out that it can be fun work, and once you're finding your groove as a programmer, then you worry less about following the rules of the language, which you have to follow, but you worry less about that and you worry more about the end product, right? Like, what problem am I solving? Does the program run and do what it's supposed to? And that's a lot more satisfying than, will it compile? So one of these days, if you're not already past it, you will get past the point where you worry, will it compile? Occasionally you'll get compiler errors still, but I'm just saying that's, you spend a lot less of your time fighting the compiler and a lot more of your time fighting problems, and that's technically at least the fun part. It's certainly the most satisfying part, is when you overcome a challenge or solve a new problem. Okay, so in your class, assembly, don't forget this coming Sunday, so October 11th, the first individual project is due. For those of you taking P&A 2 this semester, you're going to notice it's basically the same project but in a different language. So take advantage of that opportunity to just sort of see the differences based on the languages and what techniques different languages allow you to use. And it's kind of interesting to compare the same project between languages, just to see what features of the different languages you use to solve the problem. Yeah, that's smart. So Captain Price points out that where you can have the fun is you address the basic requirements and then make it your own, which is a great mindset to have. But also it's a good reminder that make sure you check the requirements and make sure that you are addressing the requirements in your program. And it is very smart, as Captain Price points out, to complete the basic project against the basic requirements, and then if there's extra things you want to add on top of that or give it some flavor, then you have plenty of time to do that. Of course, all that hinges on you being a little bit ahead of the curve so that you're not sitting there late Sunday night hoping it compiles. Instead, you get to the last few days and you think, oh, it'd be fun if I tried this thing, and then you can really sort of feel your power. And it's feeling that power, I think, which is where a lot of the fun comes from. Okay, so week 7. This is actually a fairly content-light week. But that's because it's just so weird looking what we're doing. When you see it in assembly and you sort of get how it works in assembly, it's just kind of weird looking. So I went to the week 7 module. So we're doing the x86 divide instruction, and then exploring that in the way that HLA lets you write it. But the divide, and so if you remember from last week, we did multiplication, and the weird thing about multiplication was that it's kind of hardwired to the A register, so you sort of have to be mindful of setting up your multiplication problem into the A register. So div has another layer of setup problem to contend with. So div also looks funny the way it's implemented on x86 or Intel style processors. So that's sort of the goal this week, is to get a handle on that. I'm also going to talk a little bit about sort of the traditions, the traditional or conventional uses of the A, B, C, D registers. And then we'll add in a for loop. And the reason I waited till now to use a for loop is in part because we didn't need one, but also because it looks a little bit weird in this sort of HLA/assembly style. So div, the x86 div instruction, that's the star of the show. I'm going to go ahead and go look at the content real quick, and then I'm going to spin up a sample program, and we'll sort of explore it a little bit more that way. So everything you need to know about div is in the book. It's section 10.2.2, so I'm just going to go straight there. And then just take note of some important things. So just like mul, there's sort of HLA provides some additional syntax for the div instruction. So we're going to use these three here. If I can highlight them. The two argument or the two operand form. Just like we did with mul. So we're going to use a two operand form, and they also have this sort of funny setup, except for there's a div is way awesomer than mul when it comes to what happens with, in this case, DX and AX. With 32-bit division, it's EDX:EAX. And then with 8-bit division, it says AX here, but the thing to have in your head is that it actually is talking about AH and AL. So you actually get two operations for one on Intel div instructions, which is really, really neat. That's right. So the, what do you call that part? The quotient. When you do 8-bit, unsigned 8-bit division on Intel, you actually get the quotient, the divided out part, in AL. When you do 16-bit, you get the divided out part in AX. That's right. Yeah, so it becomes smaller as opposed to potentially bigger, right? So one nice thing about division is that you're not going to get overflow because the result is always smaller than what you started with. That's right. Captain Price anticipated it. So when you do 8-bit division, you actually get the quotient and the remainder in one shot. So you're going to get the quotient in AL and the remainder of that division in AH, the modulo part. So you actually get both parts for free for doing one div on x86. If you go up to 16-bit division, then you get the quotient in AX and the remainder in DX, which is spectacular. One operation, two results. And then 32-bit division, you get the quotient in EAX and the remainder in EDX. So the trick really is, if you're interested in the remainder, you pluck off the part that you want, right? EDX or DX or AH, the upper 8 bits of the AX section of EAX. And like mul, HLA allows you to use registers for those divisions, or declared variables for those divisions, or constants. But notice that the second operand, AX, DXAX, EDX, EAX, those are hardwired. So the second operand always has to be the correct choice of those. AX for 8-bit, or DXAX for 16-bit, or EDX/EAX for 32-bit. You cannot change those. They're hardwired just like the mul instruction. That's right, Captain Price. So in the for loop on the lab, you're going to run a div, but you're going to check the remainder part to see if there is a remainder. And of course, a zero remainder is the magic, because the zero remainder tells you that that was a divisor of. So we'll do some examples, but your intuitions are correct, Captain Price. We are interested in the remainder part on our lab. And in fact, in our sample, we'll toy around with both parts a little bit. Okay, so we're not doing idiv yet. That's for signed integers. But we'll do it later, and the reason why we're doing signed later is in part because we haven't really talked about signed integers much, but also because the setup for doing signed arithmetic in some cases is different than from doing unsigned arithmetic. So we'll handle that separately. Not a constant, you'll use the counter in that for loop. So I'll show you a quick example, but you'll use the counter. Which kind of acts like a constant, but it'll be a register. Okay, so that's div. It's similar to mul. The second operand, we're going to use the two operand form. The second operand is hardwired, but we are going to use these sort of colon style arguments because there's no option, there's no way to work around that with div. With mul, HLA let us get rid of that colon, but with div it does not. So you're going to see me write examples using 8, 16, and 32-bit with the setup, and I'll remind you that you have to use the hardwired second operand. Okay, so that's div. What else we got going on? The homework, as normal, written off the readings. This week is a little bit easier in theory because there's only the one reading to work off of. The lab we're about to toy around with. But the lab is basically a very crude, a very brute force prime number checker. So we're going to check to see if numbers are prime by dividing them by every value from 1 up to and including themselves. Prime numbers will have 2 factors, 1 in themselves, and non-prime numbers will have 3 or more factors. Okay, there's that. I'll come back to the lab in a second. So we have a vote on Piazza. That's just to give you a little bit of a break. So just so you know, in case it's okay to not like HLA. There's languages that sometimes I end up using that I don't like. So for example, I actually personally don't like Python. But I wouldn't criticize it. It just, I don't like the feel of the thing when I'm working with it. I don't like it. That's just void. And there's other languages that like that for me, that I just don't like working with them. Whereas there's languages that I do like working with. Yeah. HLA I think is interesting, I would say, but I never use it outside of this class. So anyway, it's a poll. I do get a spreadsheet from Piazza that tells me who voted, but it doesn't tell me what you voted. So if you're worried that I think you're criticizing my beloved HLA language, don't worry about that. What you think is what you think based on your experience. And it's really just to give you a break so that you don't have to go out and do research. It's just to go in there on Piazza and say, hey, I'm still here, I'm still active. But I am curious to know if anybody actually likes it. My guess is that most people are going to say, I don't care one way or the other. But anyway, vote what you like. My problem with Python is that it claims to be object-oriented, but it breaks some of the rules of object orientation, like encapsulation. It breaks, but it just feels funny, and I'm not real big on the tabbing things over stuff. I mean, I get it, but it just doesn't do anything for me. Okay, so the reminders page, just the usual, and then the individual project is due on Sunday, so please get started on that. In HLA, it's going to look messy. It's going to be a mess. You may not feel comfortable using procedures, and that's fine. You don't have to use any procedures. You're going to need static variables, a bunch of them probably. But you do not have to feel like, you don't feel like you have to do anything fancy in HLA. The whole point of this is to strip away the extra layers of high-level languages and sort of get a feel for what's going on underneath. Yes, C++ does support recursion. Although I don't think it compiles, I don't think it does tail recursion very well, but I could be wrong about that. It does do recursion though. Okay, so individual project is due this week, so you might want to knock out the other work around this class. Of course, remember that you get to drop 2 assignments, so it's not the end of the world. You get to drop 2 each of discussions, labs, and homework. So if you decide this is the week to take your drops, then no harm's been done to your grade. Okay, so the lab. I'm going to come back to this because what I want to do first is just talk about div and talk about the setup for div, because it has an extra setup step. So let me set up my screen so you can see what I'm doing. Okay. So let's just go. What I'm going to do is I'm just going to spin up a little sample code using the x86 div instruction. So I can show you sort of the steps involved, and then maybe I'll sort of kickstart you on the lab like I normally do. And I always sort of apologize because I know I'm robbing you of a little bit of the fun, but since I have no time like together with you to watch you over your shoulder and sort of see what people are and are not struggling with, I feel like I need to give you a little bit better of a kickstart each week on the lab than just sort of hoping that you're going to figure it out. Although almost all of you, if not all of you, would eventually figure it out. But you have the whole individual project to figure out from a blank screen, so that's something. That's true. We could do a Zoom. I should ask about that. In fact, I should have polled about that. Oh well. I'll think of a way to ask everybody if they want me to do like a drop-in kind of Zoom thing. Okay, here we go. So, no, this is, we're on lab 7. So I'm going to call it lab 7, but initially I'm just going to do some, in fact, let's just call this a test program. And then we'll keep that separate from lab 6. Just remember when you're saving, don't just save it anywhere. Be careful that it goes desktop, assembly folder, and then I'll call this test.hla. The file names don't have to match in HLA, although it's wise to have the file name be something close. Oh, the math tutor. I forgot about the math tutor. Yes, let's do that. Thank you, Tyler. Good point. Please tell me that I saved the math tutor on here. Oh, thank goodness I did. Good idea. I forgot about that. This is great. Okay, thank you. I don't even need that other thing. The math tutor. Yes, we should do multiplication just to remind ourselves. I'll do it from scratch. So let's add multiplication, and then I will upload this to Piazza with a version 2 on it. Not program, procedure, do multiplication. So let's just review this real quick. We'll have 2 numbers. That one's misery to type. And then we'll use kind of the same setup as before, so I will move num1 to AL, and then I will mul num2 with AL, and then for the case of multiplication, we check for overflow. So that the other parts of the program, so no tricks there. We're using the HLA 2 operand form of mul here. Which is technically not an actual Intel assembly instruction, but it's there in HLA because it makes it feel more consistent with the other instructions, and it makes it a little bit easier to work with. But anyway, we'll check for overflow after that, and if we get an overflow, that we'll know that the result was too big to fit in 8 bits. Otherwise, remember that all this really means is AL equals AL times num2, right? Or AL times equals num2. That's all that means. What do I have? Show problem, get answer. Okay, so I can just repeat this whole same sequence for that. So multiplication problem, get their answer, right? Do multiplication. And then we'll compare the two. So let's do the div one, which is going to be fun, actually, if you like this kind of stuff. Okay, anyway, so mul, no big tricks. It's not that much different. The thing to keep straight in your head right now is we're doing unsigned arithmetic only. So we're only using positive numbers, right? We don't have any negatives at all in the mix. I'm making sure that you can see, which you cannot see, everything that I can see anymore. Why not? Oh, because the window shot up. Okay, now you should be able to see everything that I can see. Sorry about that. So I did the multiplication, which is very much the same, except for I'm checking for overflow after multiplication as opposed to carry. So no, the question is, does mul work with signed integers? It doesn't actually, it's imul. And the reason is because internally the processor circuitry is different for doing signed multiplication as opposed to unsigned. When it comes to add and subtraction, the processor doesn't care if it's signed or unsigned, so they're the same. But for multiplication and division, the processor actually does those differently in terms of its circuitry. So we have mul and imul for signed, and div and idiv for signed. So mul and div are for unsigned only. Good question. Okay, so there's do multiplication. I'm going to go ahead. Well, let's just do it real quick. Let's make sure it works. It probably already did it. 5 plus 3 is 8. The numbers are hard-coded, by the way. They're not random or anything. I just hard-coded the 5 and 3 into the variables. 2, and then 15. So those are all fitting, of course, because 5 times 3 easily fits inside of 255. I should have put an extra new line in there. Yeah. Just an extra new line. Okay, and then I'm kind of setting up here for div. All right, so now let's go do div, and it's quite a bit different. Is this the, what lab is this? I don't know which one you're talking about, Captain Price. Oh, we did. I did starters on Lab 6 last week, so I can't. I've already forgotten what Lab 6 is, but it might be similar. But yeah, so we'd already kind of done some of this. But I did a sample with them all, yeah, inside of the confines of the lab itself last week. Pretty sure because I always do. Okay, so let's add division. I mean, it may be working out that, oh, that's exactly what we just finished doing. Okay, so division is different. One thing to remember is that the signature looks like this. For 8-bit. Divide by zero is totally a problem, and that's one error we are going to check for just in case. So that divide by zero, I think there may actually be a flag for divide by zero, but usually we'll just pick it off in logic. So that's a good point. We're not going to have to worry about carries or overflows this time, but we are going to have to worry about divide by zero, which is technically something that no processor can do. It may, though, signal a flag. It may set a flag. Okay, so I'm just going to remind you, this is the signature of the instruction we're going to use. We're doing 8-bit division. The results, and there's two of them, go in AX. So AL will get the quotient, and AH will get the remainder. So one div gets you two results. And we'll see how to do this. But those are important to remember because it affects the setup. So we're going to have an 8-bit register, but the second operand is actually going to be 16 bits. That's in part because that's the way it's hardwired to work in Intel, but also it helps to understand that in those 16 bits you're actually getting two 8-bit results, a quotient and a remainder. So the most important thing is to pay attention to the setup, because the setup is different. So the first thing to do is to load up the numerator. That seems pretty obvious. This is going to be num1 divided by num2. So we're going to load up the numerator. Now here's the new step. It's called zero extending. It's not going to make a whole lot of sense calling it that right now, although it totally will make sense when we talk about extending with signed integers. Zero extending AX, just for now think of it as the remainder part has to be zeroed out. It just does. If you don't do this, it won't work. So you load up the numerator, that's AL, then you zero out or zero extend AH, that's the remainder part. So it has this extra setup step in it. Now we can do run the division, and that's it. But notice there's 3 setup steps now as opposed to 2 with all the others. So AL is going to get the numerator. In this case, AH is going to be zeroed out, zero extended for the remainder part. And if you skip that step, you're going to get bad results in most cases. And then the last thing is to run the division, remembering that 8-bit division has a 16-bit result register in it. The other thing that we should do, by the way, which I think is a good idea, you don't want divide by zero. So if num2 is greater than 0, then it's okay to do these things. Now in the case of add, subtract, and multiply, we just let a bad result happen, but it turns out that trying to divide by 0 is not a good thing. So yeah, so the question is, why did we zero extend? It has to do with the way the circuit actually computes this result. But if you think of it as initializing the remainder to 0, it's okay to think of it that way as long as you realize that remember that it must be done. You have to zero extend the remainder portion. When we get to signed numbers, it's going to look really weird because we're going to have to actually put all ones in there for negative numbers. So think of it as initializing the remainder to 0, but also just most importantly remember that you have to do it. you have to do this second step. You can't skimp on it. We can't because we're doing unsigned integers, remember. So for now, these have to be between 0 and 255, or they would not be uns8. So when we get to signed numbers, then we're going to have to check precisely for 0, but for unsigned numbers, it's okay to say as long as it's greater than 0. That's true. You have wraparound. So that was sort of the point of the Piazza discussion, actually, was to call your attention to the idea that if I add 1 to 255, I get 0. If I add 2 to 255, I get 1. It wraps around on itself. So it can be quite strange, and it's why we want to get in the habit of sort of remembering that can happen and maybe even checking for it. Just like if you subtract 1 from 0 and it's unsigned, it wraps back around to 255 because it can't be negative. It's unsigned. Okay, so we're just going to check for num2s that are greater than 0 because we're doing all unsigned math right now and only do the division in that case. Otherwise, we'll put out a div error message, and we will be careful to not perform the operation. In the case of add, subtract, and multiply, it doesn't hurt that we perform the operation. We just have to know that the result is a mistake. But in the case of division, we don't want to cause the processor to try to do a divide by 0, so we're actually going to prohibit it. Divide by 0 is a big no-no on computers. Okay, so there's the setup. The setup for doing division is 3 steps. 3 steps. Load the numerator. 0 extend the denominator, or the remainder part, and then run the div. So 3 setup steps. Numerator, 0 extend, division. Okay, let's go add to the quiz. Do division now. Do division. So far so good. That doesn't change anything, but it turns out that what we get for free I forgot the standard out. What we get for free here is mod. And let's see, oh, we're going to have a problem. Oh, no, we'll just do it again, I'll show you. I'll just run it again. So, going to get their answer, and then we're going to do division again, but we're going to take AH the second time for the remainder. Let's see. So the question is, does the show problem routine check those numbers? Well, the compiler does. So those 2 numbers in show problem, if those are not unsigned 8-bit integers, you'll get a compiler error. Now, if they're 8 bits and something weird, they're going to get interpreted as unsigned anyway. So it's basically impossible to get this program to compile and num1 and num2 in this routine be anything that can't be interpreted as unsigned 8-bit integers. Now, this will start to come together better for you when we do signed numbers, negatives and positives, and we'll sort of toy around with forcing the computer to interpret them as signed and unsigned. Kind of changes things a little bit. Yeah, they meant number. I'd have to look at Lab 6 to see what that is. I mean, it can. Well, actually, I have Lab 6 here. I'll just open it. Get number. Yeah, if min or max aren't 8-bit, you'll get a compiler error for sure. This is a reason to like compiled languages, by the way. Compiled languages catch big mistakes like this at compile time so you can fix them. Yeah, this won't compile if either of those numbers, if min is negative or bigger than 255, you should get a compiler error. Oh, no, that's going to crash. So I assume you're asking, so someone's asking like, on this get U8, I'll just do it and show you. If you try to input something that's not an unsigned 8-bit integer, the program's going to crash. But that's by design. HLA does that on purpose because if you want an unsigned 8-bit integer and they type 256, well, what is it supposed to do with that? So it crashes. I'll add it to my sample so you can see. It should just crash. Not a compiler error, just a crash for that. I don't know what, I'm not sure what that is referring to. If you submitted Lab 6, I'll see it. I would have to see that for myself. I'm not sure. So someone's asking a question if you're watching the video later about a compiler error on Lab 6 that has to do with this procedure. The only way it's going to cause a compiler error, there's two things I think that would obviously cause a compiler error. One is you're trying to call this procedure without a string and an unsate and an unsate. The other would be down here at the breakif. If you're comparing AL to something that's not 8 bits, you'll get a compiler error. If you're comparing AL to something that's not 8 bits, you'll get a compiler error. So the HLA compiler is checking the sizes of things. Other than that, I'm not sure what it might be. Okay, so here's the math tutor. So I can finish that thought. I wanted to show you, though, getting the remainder, which in a lot of high-level languages is the mod operator. It's the same division problem, it's just a matter of which piece do I take. So if I want to know the remainder, I take the AH part from the division. If I want to know the quotient, I take the AL part. So I'm going to take my own quiz here. 5 plus 3 is 8. 5 minus 3 is 2. 5 times 3 is 15. 5 divided by 3 with integers. 3 goes into 5 once. 5 mod 3, so what's left over after I take the 3's out is 2. So that's the division thing working. It shouldn't crash on adding. It's not going to crash. If you add two numbers that don't fit in unsate, it won't crash unless the sizes don't match. I mean, I can prove it right now. Now, if you're getting compiler errors, you sort of need to look at the lines that are being referenced. You need to check things like, do the sizes of things match? But let's just see what happens here as an example. So if I'm just going to test an integer. I'm just going to put a num in here and call it unsate. The point of my experiment right now is to see, can I get a compiler error to happen? Put two new lines there. So let's just see. And this is a kind of like a recommended experiment, by the way. If I look at a procedure and I realize it wants an unsate, one thing to test is the limits. So an UNS8 should accept a 0. It should accept a 255. Now let's see what happens if I test beyond the limits. Actually, let's comment that out and make sure that it works for the limits first. Okay, so there's the 0 and 255. So what I'm doing here is I'm testing the limits, because if I pass a -1, let's see what it does with that. Okay, so Captain Price gets a, so there you go. I immediately get a compiler error. It's referencing line 17. So the type does not agree with the type of the formal parameter. So it's saying this, the type of this -1 doesn't match the type of this parameter. So that's good, because an UNS8 can't be -1, so we want a compiler error to happen. Let's try 256. See if it's checking. Yeah, same thing. So the compiler will in fact catch it. That also works, by the way, if you try to pass in, so AX is 16 bits. Shouldn't work. Should get a compiler error. And I do. The size does not match. Now if I put in something that the size does match, like CL, it should be perfectly happy with that. That's going to be unknown garbage data, by the way. Turns out it was 0 at the time. So if you're getting a compiler error, these you may not at present be able to make sense of, but look for the line number reference and start matching things up in terms of their sizes and their limits. But that said, you can totally do this. I'm going to do something slightly wrong here. See if and it's not wrong, but it's something to pay attention to. So I'm going to do something that's a little weird, and it's something you want to be on the lookout for and try to not do in your own code. So it's going to work, but it's going to be a little bit weird. The sequencing. Okay, so +2 equals. So take a look at that line and think for a second about what it is I'm doing that the output might look a little bit strange to someone. That's a register, so it should be, AL's the middleman, so I load up 255, I add 2 to it. That's not possible, so what happens? What? Oh, there. Shows up as 1. Yeah, it shows up as 1. Now the other thing, and the reason why it shows up as 1 is because the way it's working is 255 plus 2. Well, 255 plus 1 wraps around to 0, and then 1 more than that wraps around to 1. So it overflows, although we'll check for... you can check carry or overflow in that case, although I think technically we check carry. Did anyone notice something funny about my output, by the way? Why is there a 0 in front of it? There's something not quite right there. There you go. Nice one, Glazer. So by default, those registers come out in hex. So pay attention for that, because unless you're purposely printing out hex, which occasionally we are, you need to typecast it. So I need that to be an UNS8, so that it comes out as decimal. So I'm going to change this to, let's say, 10. And see if we can predict, so again, sort of predict what you think it's going to wrap around to. it cannot, technically it should be 265, right? But it can't be because they're unsigned 8-bit integers, which top out at 255, and adding too much causes it to wrap back around from the start. So I'm going to compile this. And then it's going to wrap around to something. Is it 8? 9. One more. 255 to 0. Yeah. So to 9. I can't do those in my head, actually. I always have to run it and see. So it wrapped around to 9. So 1 took it to back around to 0, and then 9 more on top of that. Same thing happens, by the way. If we go in the other direction. So if I subtract 2, well, it can't be negative 2 because they're unsigned. But you're going to notice it's going to wrap around to 255 and then however much further it goes from there. So 0 minus 1 caused it to wrap around to 255, and then the one more on top of that drew it back to 254, which is wrong, of course, but that's, so it doesn't cause errors in terms of the compiler, but it does cause errors in terms of the result, which is why we do those carry checks on this kind of math, because the processor is more than happy to run the circuit, it just, the answer is wrong. Yeah, the compiler is satisfied. The compiler only cares about the basic rules, right? Do the sizes match? But the compiler really has no way to know how that's going to compute, so it can't check it. Yeah, so in terms of the processor arithmetic, it's wrong, but in terms of the programming language rules, there's nothing wrong with it. Because 0 is fine for an unsigned, 2 is fine. You can subtract one unsigned number from another unsigned number. It just turns out that if you're not careful as a program, it's going to wrap around. By the way, this also happens in high-level languages. Try this in C++. You'll have to figure out how big your integers are. But if you do an unsigned integer in C++, it'll probably be a 32-bit integer. And then you can sort of fart around with the limits, and you'll discover that it does the same thing. So you can cause the same problem in C++. It'll compile, but then when it computes the answer, it'll be wrong because it ran off one of the ends in terms of the data type. So this is one of the useful insights to have in this class, is to understand the limits of things like integer arithmetic and how easy it is to have bad calculations enter into your code. Okay, so let's do some division in here. And I'll do 3 different ones. So I'm going to do standard out.put. I'm going to do a little, let's see if it's even number. But I just want to show you something when I run this program real quick, so that you're aware of this happening as well. So standard in.getU8, that's the HLA standard library getting an unsigned 8-bit integer. But let's see what happens if I try to be cute. Okay, so I'll put in a negative, my numlock's not. I'll put in a -1. So this HLA exception, that's on purpose. It says conversion error. Now we're going to eventually write code to handle that, but I put in something that's not an unsigned 8-bit integer, and HLA just stopped on that, halted the whole program. That's by design. So if you're seeing these exceptions, that's user error. Now we will code for that, but for now we're not coding for it. We just need to be aware of it happening. Same thing is going to happen if I put 256, by the way. This time, instead of conversion error, since it can't convert a negative number to an unsigned number, I get a value out of range error. That's HLA again doing that, and that's by design. It just halts the program because it can't fix that problem for itself. I can also cause that to happen if I put in just something weird, like my name. It can't convert that into an unsigned 8-bit integer. So just to be aware of those things, for now we haven't coded to get rid of that problem. But what I'm going to do is I'm going to check it to see if it is an even number. And hopefully everyone knows that an even number is something that's evenly divisible by 2. So let's do that. We have our number in AL. It's already there. So step 1, the numerator has already been loaded up for me. Step 1's already been done by this get U8. That's right, modulo 2. And we're going to do divide and then check the remainder, right? So step 1's already been done. Step 2, zero extend to AH. Have to do that or the divide just won't work. Step 3, run the div. And now we do what Captain Price was talking about. If we want to know if my input is even, then the remainder should be 0. And the remainder is in H. If it's not even, by the way, then it must be odd. So the remainder, which for 8 bits is in AH, right? The quotient is in AL, the remainder's in AH. One thing to note here, by the way, is that the division is going to destroy my original AL. That'll have the quotient. So I no longer have their input on hold. And if there's a reason why you want that input, then you need to make a copy of it. So one thing you could do is just move AL to BL. So that I can come back later and say, hey, that thing you input, BL. We know the remainder's in AH because that's what the Intel documentation says it does. So the remainder's in AH because the Intel processor is hardwired to do that. It puts the quotient in AL and the remainder in AH by design, by definition. You can't move those around. You can't change where the remainder goes. It always goes into AH for 8-bit, always. So that's a good question. How do we know it's there? Because Intel says it's there. And if it's not, then Intel made a mistake, not us. But it'll be there. All right, so I'm going to make a input. I just wanted to point out to you that sometimes you need an extra register or an extra variable if you want to not lose stuff. So because the division is destructive on AX, it changes the data that's in there. My original input's going to get lost if I don't make a copy of it. Something to think about. Yes. So another question is, so we will always zero extend into AH? Yes, for 8-bit division. So I'm going to do the 16 and the 32s also, just so you've seen those. But the answer is yes. Always AH for unsigned 8-bit division. Always. You always zero extend it, and you always get the remainder in it. Now let's run that real quick. This is test program. So I'll just do a 100 should be even, right? and then 101 should be odd. So we could have printed out the AH and the AL just to see what they had in them, but we assumed. So let's change this. I'm going to move this section out of the way. And let's do 16 and then 32-bit. So 16-bit range, 16, use 16. Okay, so step 1 has already been done. Now the numerator is in AX. For 16 bits, the numerator goes into AX. Now, step 2. We zero extend DX this time. The reason why is because DX is hardwired for 16-bit unsigned integer division in Intel. DX is hardwired to be the remainder part. So I'm going to divide that by 2. That is how it's written. That is just how it's written. That's how the Intel engineers designed it at some point in the past. That is how it always has to work. For unsigned 16-bit division, the remainder slash the part that needs to be zero extended is DX. You run the division as DX colon AX, understanding that DX represents where the remainder goes, AX represents where the quotient goes. This time I'll just say, I'll just do it like this. The quotient equals, and then I'll type these to 16-bit. So the quotient's in AX. The remainder equals in DX. By definition, you can't change it. That's the way it works. So it's always for 16-bit division, which is what we're doing here, 16-bit number. And we're going to divide it by 2 and see what the quotient of that and the remainder are. I don't know. 1, 2, 3, 4. So the quotient when 9999 is divided by 2 is 4999, and the remainder is 1, as expected. So those are hardwired. You cannot change them. And then you might guess, take that and put it down at the bottom. I don't remember where this goes. Somewhere way up there. I don't remember that number off the top of my head, so I'll just say you can enter a big one now. Okay, so EAX now, the numerator. So my numerator is already loaded by the get. So now for 32-bit division, the remainder slash thing that has to be zero extended is EDX. Has to be that way. It's hardwired into the circuit on your processor, and then the div, whatever, I'll divide it by 3, let's say, just for fun. Has to be that. Has to be EDX colon EAX. So for 32 bits, the remainder goes into EDX, the quotient goes into EAX. I'm going to copy and paste some stuff for myself because I don't feel like typing all that over again. This time it's going to be uns 32s. And the result registers are the bigger ones now. Did I save? I did save. Whatever. 1, 2, 3, 4, 5, 6, 7. Because there's a 3 in there. That's interesting. Yeah, that makes sense, because that would have been one left after the 6. Okay, anyway, there's 32 bits. So this takes some practice. You got to remember that there's 3 setup steps now. There used to be just 2. Middleman, math, right? That's the old 2. Middleman, do the math. Now it's middleman, 0 extend, do the math. The 3rd step when you're doing division. The upside is that you get one division instruction gives you 2 answers, the quotient and the remainder, which is pretty cool. Okay, so now I need to get, what am I doing on time? So let's just go have a peek at Lab 7, and so I can feel confident that you have a good starting place. So I'm just going to show you real quick that I'm going to, I'm on the lab assignment here. I think you can see that. Yeah. I'm on the lab assignment, so I'm just going to go pop open this code. Go to the raw, because this is faster. And then Control A, Control C. And now I'm going to go back to lab 7.hla. It's already in my assembly folder, so that's nice. Okay, so let's just have a peek through here real quick and make sure we're all okay. So here's something to notice. The user input's going to be 16 bits now, so we have to think about that, and I'll remind you when we see the division section, 16 bits. So the get number, the min and the max can go up to as far as 16-bit numbers can go. And then you'll do the same get number routine. You just have to be careful that you're doing a get U16 this time, because that's what this lab is working with, the 16-bit numbers. And that's just to give you practice with the different sizes so that you have to think about it a little bit. Otherwise, the get number is the same as you've seen in multiple labs leading up to this week. The go again procedure, that's the number 2 item, which you've seen a whole bunch of times now, so just go grab it and stick it in here. But I thought maybe it would sort of help your confidence a little bit if you're like, oh, it's my own code from a prior lab. Alright, so the big star is this show factors thing. So I'm just going to show you the for loop that I've already written in here. And remind you about things to consider. There's different sizes of data going on in here. So the math is all being done with 16-bit integers. This factor counter is just an 8-bit integer. Because I don't imagine that we're going to have any numbers that are so huge that they're going to have more than 255 factors. If you do that, then I guess good for you, but it's not likely that you're going to find one of those in a 16-bit unsigned integer. So this procedure is the star of the show. Its job is to count all the factors of a number. And the way it does that is it divides that number by every number from 1 up to including itself. And for every one of those divisions where there's 0 remainder, it has to count that as a factor. Right, so I'll just give you, let me do one more new. So if we want to know, like, how many, oops, caps lock is on. How many factors does 27 have? What our program is going to do is it's going to say 27 divided by 1, and really mod 1. And then I'm going to paste this a whole bunch of times. up to around 30 or so. So this is what our program is going to do. It's going to use a loop to generate all these numbers. So 1, 2, 3, 4, 5, 6, 7. This is going to take me a while, but this is what our program is going to do. The loop is going to generate the numbers from 1, 2, 3, 4, 5, all the way up to 27. So in the Lab 7 code, this loop right here is generating using CX as a counter. Now the reason why it's using CX is because that's 16 bits. The number is 16 bits and all the math is going to be done in 16 bits. So if we start a counter at 1, this is how you do a for loop in HLA. If you start a counter at 1, CX equals 1. Go all the way up to and including the number, incrementing CX. So it turns out that Intel has an increment instruction. I just didn't show it to you yet because I wanted you to get comfortable with add. Increment adds 1. So you could also do an add 1 instruction here, but that's an add 1 instruction. Oh yeah, thank you, Glazer. I didn't see the question. So yeah, if you want to undo something, you can Control Z. Well, which should be true in every editor you ever use, I think. All right, so CX. So hopefully you understand that this 1, 2, 3, 4, 5, 6, 7 through 27, that's CX. So we're actually, so the model here is the number mod CX. 27 is the number, and this other value is the CX as it's counting up or being incremented through the loop. So this is what we're really doing, is this. So what does it actually though mean to do number mod CX? Well, it means to move the number to AX, the numerator, right? That's not, this is just notes. So we move the number to AX, which is that first step. We load the numerator into AX, and it's AX because the number is 16 bits. So we're doing 16-bit division, which means we're going to zero extend what? As the second step. So does anyone know what, for 16-bit division, what gets 0 extended into? What's the remainder go into? For 16-bit division, which is what the lab does. Not BX, but we're close. There we go, DX. Okay, so now we get down to running the div. So you kind of have to look at line 3 here and then think about what goes here when we run the div. What are we dividing by? What's the divisor, in other words? CX, good. CX, that's what we're dividing by. So we're dividing by 1 and then 2 and then 3 and then 4, and that's what CX represents. And then the last part of the setup is what goes, what's the second operand for 16-bit unsigned division on Intel. This one looks funky. There's a hint there because there's 5 question marks. There we go. DX, AX, good one. So there's the setup, and then what we're interested in right after the div is something having 0, which tells us no remainder, in which case we'd increment add 1 to factor count. So the last one for the sort of hints is, what are we looking at? What do we care about it being 0? Yes, DX, good one. DX, that's the remainder part. So that's the part we zero out is the remainder part, and that's the part we care about. That tells us that there was a factor there. Okay, so that was good. That's the whole setup. Hopefully that explains a little bit the algorithm that we're using. Oh, that's all the window that I have. Hopefully that explains a little bit the algorithm that we're using. So we're given a number as a parameter. We're using the for loop to generate the divisors, 1 through whatever the number is. So we just did this, right? Set up the numerator, 0 extend dx for the remainder, run the div, and then check the remainder. It says print. Go ahead and print out the value and increment the factor counter. So that was what I just did in note form on the other page. In kind of pseudocode form was those steps. Load the numerator. 0 extend for the remainder. Run the div. And then check the remainder. Do a printout of the number and also increment the factor counter. And then the last step is, I'll just do that one for you. So the last thing that the procedure does is it puts the final factor counter into AL as its result. So it's been counting the whole time. How many factors does it have? All right, so that's that one. And then number 8 is a check. So we call this procedure show factors, and then immediately afterward we check AL, which is where that count of factors was placed by the procedure. If it's 2, we have a prime number. Pseudocode, but that's the whole thing. So you check after show factors runs, it's going to leave the count of the number of factors you computed in AL, and then you can use that because prime numbers will only have 2 factors, 1 in themselves. Non-prime numbers will have more than 2. Okay, I gave you a little bit less to work with this time inside of the code itself. If you're watching the video later, right before we looked at this code, I did some notes and we worked up this algorithm in pseudocode, and we also discussed what is this CX doing. This is the kind of the scariest one to look at in terms of assembly code so far. And I also know that you have the project to do, so hopefully you manage your time well and you don't feel overwhelmed by those things. But this isn't very much, it's just a little bit more confusing than normal. It's all here in the video in pseudocode or some other form. So hopefully that's enough for you to do good. If you need help on the project or on this lab, please don't ignore Piazza as a resource. If you put notes on Piazza, if you put a question on Piazza and someone answers it, then everybody can benefit by it. And you can do that anonymously if you're shy about such things, but you can sort of share the answer with everybody if you put it in Piazza. So please consider doing that for both project questions and lab questions. Okay, otherwise I think I'm done. So hope you have a good week. Hope the project goes smoothly. If you need to contact me by Canvas inbox, please do so. If you can overcome your shyness about it, please consider using Piazza. I check it every day, and you can get an answer there and then other people that may help them out as well. Thank you, Tyler. Appreciate it. If you're in PNA 2, I'll see you again tomorrow evening. Otherwise, I will see everyone again on Monday next week, at which point we're almost officially halfway there after next week. So we're getting there. I will upload Math Tutor, by the way, to Piazza with the version 2 on it, so you can see that. Okay, everybody take care. Have a good week, and I will see you next week. Goodbye.